Welcome to a lesson with Dr. Powell. Let's take a look at why the curl of a vector field might be called the curl of a vector field. So suppose that we have a vector field F, and we have a curve that wraps around going counterclockwise like this. And we have think of taking a line integral, and that's done by taking a dot product of dr and f. It's kind of like projection, even like how much does f really like go flow maybe around. If it's anti-flowing, you subtract. If it's flowing, you add. But overall, the effect kind of is like how much is f really going along the curve as I wrap around. So that's kind of an idea that we use. Now, in order to find that, we can use Green's theorem, take the curl and then do a double integral over that. The curl itself, if we work through it, gives you just a dx dy, which, if you think about differential two forms, is just the z component of a differential two form. So it's actually orthogonal to the xy plane. So it's a vector that's pointing up or down, but really the value of it is what we're interested in. Is its value pointing up? Is its value pointing down? And how much is it? Is it a lot or is it little? I mean, if it's a lot, that means that that on this path as we go along here, we're really going to pick up a lot of as we move around here in our dot products for how the vector field is going along this. Now, keep in mind that the curl is going to be the same at a point no matter what path we choose. So if our vector field kind of tends to really be all one directional, we take a path through it, what's going to happen? When we take a dot product here on one part, it's going to be, if we take a dot product over here versus over here, when we're going one direction or that direction, it's really the negative of it, and it really cancels. It's almost like you have a zero curl. However, if your vector field tends to be moving and changing, then of course, as you get smaller and smaller line integrals, the result might be smaller just because you're looking at a smaller place. But as you get bigger, it should reflect the curl of the vector is like you're basically integrating that over that area, should reflect the idea of how much it's curving, turning, going around in some sense. So curl really does, since it relates directly to the output of a line integral where you wrap all the way around in a loop, that's why it's maybe called the curl. It kind of gives you a sense for how your line integrals are going to go around like this. So are the vectors themselves in the vector field wrapping around along a curve or not? Hence the name curl. Thanks for watching.